Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. We are presently studying marine boilers. In this lecture, we will go through the following topics. First, we will look at why cylindrical pressure vessels are commonly used as boiler drum and what are their advantages. Next, we will discuss circumferential stresses in a cylindrical drum and how they can lead to failure. After that, we will see how longitudinal stresses affect the drum and may cause rupture. Then we will look at how stresses are related to steam pressure, drum diameter and thickness. We will also talk about the steps that can be taken to reduce these stresses in a boiler. Next, we will go over the stresses in the end covers. Finally, we will compare cylindrical drum covers with disc ends and flat ends. Let's go through these one by one in the next slides. Advantages of cylindrical pressure vessel. Cylindrical pressure vessels are preferred over other shapes for the following reasons. Uniform pressure distribution reduces stress concentration. In a cylindrical vessel, the stresses caused by internal pressure are more uniformly distributed compared to other shapes, which reduces stress concentration and the risk of material failure. The continuous curve in cylindrical vessels without sharp changes enhances the overall strength. Offers stable and predictable design. The cylindrical shape is efficient in withstanding internal pressure, making the design more stable and predictable under pressure. Offers cost-effective and simple construction. Cylindrical pressure vessels are more cost-effective compared to other shapes and are easier to fabricate. Rolling metal sheets and welding them together is simpler than fabricating complex shapes. Additionally, cylindrical vessels are easier to inspect and maintain. Provides higher strength to weight ratio. In a cylindrical shell, internal pressure exerts uniform forces across the surfaces, leading to an even distribution of stress along the walls. This allows for efficient use of material, resulting in a higher strength to weight ratio. In contrast, corners and flat surfaces in other shapes, such as rectangular or cubic vessels, tend to experience higher localized stresses, resulting in stress concentrations. These areas are more prone to deformation and failure, requiring additional material for reinforcement to achieve the same strength, which ultimately makes them heavier. Offers excellent resistance to buckling. Cylindrical shells offer excellent resistance to buckling under internal pressure. The curvature of the shell provides inherent stability against buckling, a common failure mode in pressure vessels. Flat surfaces in non-cylindrical shapes are more prone to buckling under pressure. To prevent buckling, these shapes require thicker walls or internal stiffeners which make them heavier. Improves structural integrity under internal or external pressure. Cylindrical vessels have better structural integrity under both internal and external pressure, which is particularly important for high pressure applications, where safety and reliability are of paramount importance. Apart from the other advantages, cylindrical shapes are scalable, making it easier to apply design principles uniformly across different sizes of pressure vessels during production and application. Effect of circumferential stresses in cylindrical drum. Various stresses develop in the boiler drum due to the force exerted by steam pressure. A boiler should be designed so that its material can withstand these stresses and serve the intended life of the ship, which is usually around 25 years. It is important to understand the value of these stresses when designing a pressure vessel, such as a boiler drum. Care must also be taken to prevent excessive loss of strength caused by cutting holes in the drum for fitting tubes and mountings. The boiler drum is made by rolling at least two plates into a round shape and joining them with double butt welds along the longitudinal axis. Let us now look at the important dimensions of the boiler drum that are used in stress calculations. Internal diameter of the drum D. Length of the cylindrical drum L. Thickness of the drum T. The steam pressure inside the drum P exerts a uniform force on the inner surface. This sets up circumferential stresses in the boiler drum. If these stresses exceed the strength of the resisting material, the drum may rupture along the longitudinal direction as shown by the shaded area. In the next slide, we will calculate the value of circumferential stresses. Since the internal pressure acts uniformly in all directions, circumferential stresses are set up in the shell. If these stresses exceed the strength of the resisting material, the shell may rupture longitudinally. Rupturing circumferential force is equal to pressure into projected area is equal to P into D into L. Resisting force of the longitudinal seam is equal to stress into area of the resisting material, which is equal to sigma into 2 into L into T. By equating these two, we get circumferential stress sigma is equal to PD by 2T. Effect of longitudinal stresses in cylindrical drum. For the same boiler dimensions, this sketch shows how longitudinal stresses are set up in the boiler drum due to the force of the steam acting on the end covers. If these stresses exceed the strength of the resisting material, the boiler shell may rupture circumferentially, as shown by the shaded area. In the next slide, we will calculate the value of longitudinal stresses. Rupturing longitudinal force is equal to pressure into projected area, which is equal to P into pi into d square by 4. Resisting force of the circumferential seam is equal to stress into area of the resisting material, which is equal to sigma into pi into d into t. Equating above two equations, we get longitudinal stress sigma is equal to Pd by 4T. Relationship of stresses with steam pressure, drum diameter and thickness. We know that circumferential stress sigma is equal to Pd by 2T. Since stress is directly proportional to pressure, a boiler drum must be carefully designed to withstand the working pressure with the required safety margins. Water tube boilers are generally used for high pressure, while smoke tube boilers are suitable for low pressures. Because stress is directly proportional to diameter, the shell diameter should be limited and the cylindrical length can be increased instead. In high pressure water tube boilers, the tube diameter is kept small to limit stresses. This also helps reduce the required wall thickness. In smoke tube boilers, the furnace is surrounded by water and is therefore subjected to external pressure. Since the furnace diameter is much larger than the tube diameters, smoke tube boilers cannot be used for high pressures. To limit stresses, the furnace of smoke tube boiler must be made compact. Finally, since stress is inversely proportional to thickness, the drum should have sufficient wall thickness to safely withstand the steam pressure. Measures to reduce stresses in the boiler. We have seen that circumferential or hoop stress are double that of the longitudinal stresses. Considering higher factor of safety for boiler design. For boiler safety, the shell is therefore designed to withstand the higher stress, that is, the circumferential stress. A minimum factor of safety of 6 is taken to allow for material wastage due to corrosion and for possible lack of homogeneity in the material. Consider small holes for boiler mountings. During boiler erection, several holes need to be cut in the shell for attaching tubes and mountings. Care must be taken to keep these cutting to a minimum. Consider elliptical manholes and handholds. Elliptical manholes and handholds are preferred over circular ones as they require less cutting of the material and also provide other advantages. Since circumferential stresses cause rupture along the longitudinal direction, the minor axis of the elliptical cover should be placed longitudinally. Compensate for loss of strength. The loss of strength caused by cutting holes must be compensated either by increasing the thickness of the tube plate or by fitting compensating rings on the wrapper plate. Stresses in the boiler and cover. The figure shows that when pressure acts on the flat plate, it causes the plate to bend until equilibrium is reached. To resist the bursting force, internal stresses are developed in the plate. These stresses can be resolved into perpendicular components, one of which opposes the applied force. The plate surface continues to bend until this opposing component balances the pressure and it finally takes the shape of an arc of a circle. Boiler drums with spherical and flat end covers. This sketch shows a drum for a large boiler with dished ends and a drum for tank type boiler with flat ends. Dished or spherical end plates are preferred in pressure vessels because they provide much higher strength and structural efficiency. This is due to the uniform distribution of stress, unlike flat end plates of the same thickness. Dished ends are essentially self-supporting. High pressure boiler shells on the steam ships are therefore fitted with dished ends. When a flat end plate is subjected to internal pressure, the stress distribution across the plate is non-uniform. The central portion experiences high bending stresses, making it more prone to deformation and failure. To prevent this, flat end covers must be made sufficiently thick and supported by stays. This support may be provided by solid stays, stay tubes, or plate girders. The figure shows end plate supported by solid bars welded with washers. Low pressure boilers used on motor vessels are usually of the tank type with a vertical layout. The bottom end may be flat, but the top of the drum is usually dome shaped. This completes our study of advantages of using cylindrical vessels as boiler drum, effect of circumferential and longitudinal stresses in boiler drums, relationship of stresses with steam pressure, boiler diameter and thickness, measures that can be taken to reduce stresses in boiler drum, stresses in boiler end covers, and comparison of boiler drums with spherical and flat end covers. This book has been written by me and covers all the topics as per Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in examinations conducted by Indian Maritime University. It will help students prepare effectively for exams and also support them in working safely with ships' boilers. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found the tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thanks for watching till the end.